Hello dear students, today we are going to explore another important resilience pattern known as the bulkhead. And as always, we'll go beyond the theory. I'll guide you through a practical implementation using the Resilience4j library integrated into a Spring Boot application, so you can see exactly how this pattern works in action. So, here's what we'll be covering in today's lesson. We'll start by exploring what the bulkhead pattern is and why it plays such a critical role in building resilient systems. Then I'll walk you through several real-world scenarios where applying bulkheads helps prevent cascading failures and keeps services isolated under stress. Next, we'll compare the two main types of bulkheads, semaphore-based and thread pool-based, and discuss when to use each. Once the theory is clear, I'll explain how Resilience4j implements bulkhead control and how you can easily integrate it into your Spring Boot application. After that, we'll dive into a hands-on demo. I'll show you real code examples that demonstrate how bulkheads behave, how fallback works, and how you can test their limits in action. And finally, we'll wrap up with a set of best practices to help you apply bulkheads effectively in a real microservices architecture. Let's get started. Let's begin today's session by introducing a resilience pattern that plays a crucial role in protecting modern applications from cascading failures. The bulkhead pattern. The concept, as you might guess from its name, is borrowed from naval architecture. On a ship, bulkheads are physical partitions that divide the hull into separate compartments. If one compartment takes on water, the others remain sealed and operational, preventing the entire ship from sinking. In software, we apply the same principle to isolate parts of our system, so that if one component becomes slow, overloaded, or fails entirely, it doesn't bring everything else down with it. Now, why does this matter? In a typical microservice or even a layered monolith, different parts of the system handle different types of workloads. Some calls might be to fast, reliable components, while others may involve external services that are slow or occasionally unavailable. Without bulkheads, all these calls could end up sharing the same thread pool or system resources. And if one part of the system starts consuming all the available threads, let's say due to latency or high load, then every other part that depends on those threads begins to fail, even if they are functioning correctly in isolation. The bulkhead pattern helps us avoid that. It enforces resource partitioning. It limits how many concurrent calls or threads each part of the system can use, thereby containing the impact of failures. Instead of letting one troubled component overwhelm the system, we say, you can have this much, no more. The rest of the system remains responsive even when some parts are under stress. So, in a world where services are interconnected and failure in one place can ripple outward in unpredictable ways, the bulkhead pattern provides a strong line of defense. It's not just about resilience, it's about intelligent isolation, controlled resource sharing, and ultimately building systems that remain usable even under partial failure. Now that we have grasped the concept of the bulkhead pattern, let's ground it in real-world scenarios where it truly proves its value. Picture a web application that handles both user-facing operations and background processing tasks. These two types of operations often have very different behaviors. User requests demand speed and responsiveness, while background jobs may take longer, consume more resources, and tolerate some delay. But if both sets of operations run on the same thread pool or share the same resources without boundaries, a surge in background jobs can choke the system. Suddenly, user requests slow down or fail, not because they are broken, but because they are blocked by another component. Or consider a microservices architecture where multiple services make calls to external systems. Perhaps one service communicates with a payment provider, while another retrieves product recommendations. If those calls all use the same pool of threads and the payment provider becomes sluggish or unresponsive, it might hold on to threads much longer than expected. In such a case, even unrelated services start to experience timeouts. simply because they can no longer access available threads. What should have been an isolated delay now becomes a system-wide slowdown. Another common scenario is with APIs that expose both public and internal endpoints. Suppose an internal batch job suddenly floods the system with traffic, unintentionally consuming all available capacity. Without bulkheads, public users also feel the impact. But with bulkheads in place, internal and external traffic are isolated, allowing one to struggle without affecting the other. In all of these cases, the bulkhead pattern offers a clear and elegant solution: divide and contain. By creating boundaries between workloads, between services, or even between different types of calls within the same service, we protect the overall health of the system. We make sure that one overloaded component doesn't drag everything down with it. And that kind of isolation, when implemented correctly, becomes a cornerstone of high availability architecture. Now that we have seen why bulkheads are important in real systems, let's take a moment to understand the two main types of bulkhead implementations you'll encounter: thread pool isolation and semaphore isolation. Both serve the same purpose: limiting concurrent access to protect resources, but they do it in slightly different ways, each with its own trade-offs. Thread pool isolation is perhaps the more heavyweight of the two, but also more robust in certain situations. In this model, each protected component gets its own dedicated thread pool. So when a call is made, it's handed off to a separate thread from that pool. If the pool is full, meaning all threads are busy, then new calls are executed or rejected depending on the configuration. The key advantage here is that it provides true concurrency isolation. Even if one service starts to lag or block, it won't tie up the threads used by others. This is ideal when you're dealing with operations that might be slow or blocking, such as input-output bound tasks or calls to external systems. Semaphore isolation, on the other hand, is a lighter and more efficient approach. It doesn't use separate threads. Instead, it limits the number of concurrent executions within the caller's thread. Think of it as placing a turnstile at the entrance of a method. Only a certain number of callers are allowed through at a time. If the limit is reached, new calls are either blocked or redirected to a fallback. Since no thread switching is involved, semaphore isolation introduces less overhead, which makes it suitable for CPU-bound or short-lived operations where performance is critical. So which should you use? That depends on the nature of your workload. If you are calling remote services or working with blocking input-output, thread pool isolation can prevent those delays from affecting the rest of your system. But if your operations are fast and resource-light, semaphore isolation may be the simpler, more efficient choice. In either case, both patterns align with the same principle. Don't let one part of your system monopolize shared resources. And in Resilience4j, you'll find support for both models, giving you the flexibility to choose what's most appropriate for your specific use case. Now that we've distinguished the types of bulkhead isolation, semaphore and thread pool, let's look at how Resilience4j actually implements these mechanisms in practice. Resilience4j, as you know, is designed to offer focused modular tools for resilience, and its bulkhead module reflects that same design philosophy. It provides two distinct implementations out of the box, one for semaphore-based isolation and another called thread pool bulkhead for thread pool isolation. Let's start with the semaphore-based approach. In this model, Resilience4j creates a bulkhead that limits the number of concurrent calls allowed to a given method. When a method annotated with a bulkhead is invoked, Resilience4j checks how many concurrent executions are already in progress. If the number is below the limit, the call proceeds immediately. If the limit has been reached, the call is either rejected or directed to a fallback method, depending on your configuration. What's important here is that the execution happens on the caller's thread, which makes it fast and resource efficient. However, it also means that if the task itself blocks or hangs, it will still occupy that calling thread. So this type of bulkhead is best suited for short, non-blocking operations. Now let's consider the thread pool bulkhead. This is designed for asynchronous operations, often using completable future. When you use this model, Resilience4j assigns a dedicated thread pool to the protected method. Calls are submitted to this pool, and if all threads are busy and the queue is full, new requests are rejected. This adds a layer of isolation between the caller and the callee, because execution happens on a separate thread. And it's ideal when your method performs blocking input-output operation or interacts with unreliable external systems. It helps ensure that even if those calls are delayed, they won't consume the threads used by other parts of your application. In both cases, Resilience4j lets you configure parameters like the maximum number of concurrent calls, the size of the waiting queue, and even fallback methods for when the system is overloaded. These configurations can be set in your application properties or programmatically, and they allow you to tailor the bulkhead behavior to the needs of each individual component. Okay team, we've covered enough theory, so now it's time to switch to practice. I've prepared live code examples for you, and I'll walk you through them step by step to give you a clear understanding of how you can implement the bulkhead pattern using Resilience4j in a Spring Boot application. Let's see how it works in action. Team, before we start a review, I want to say that all the source code examples are available in the attachments to this lesson. I'll walk you through each line of code and explain everything step by step. But if you have any questions, feel free to leave a comment under the video and I'll be happy to help. This is a demo project based on Spring Boot. I've created dedicated packages for different examples. In addition, I've added a few configurations and dependencies to support the demo. I will share with you all the necessary details. Let me start by opening the pom.xml file and showing you which dependencies I've added. Now, before we dive into the code, let me quickly point out that in the pom.xml I've added the necessary dependency for Resilience4j library. It's a focused module specifically designed to work with Spring Boot. This dependency gives us everything we need to enable annotation-based resilience features in our application. Now let's take a closer look at this bulkhead service class and understand how it demonstrates semaphore-based bulkhead control in Resilience4j. This class is a simple Spring service, and it contains a method called process_sync_request, which we've marked with the bulkhead annotation. That annotation is doing all the heavy lifting. It links this method to a specific bulkhead configuration, identified here by the name backend_sync. So what happens when this method is called? Well, inside the method, we simulate a delay using time unit second sleep. That pause represents some slow or resource-intensive operation, perhaps a database query, an external API call, or simply a computation that takes time. The important part is that this method holds onto its thread for 3 seconds every time it's invoked. Now, with the bulkhead in place, Resilience4j controls how many of these calls can run at the same time. If the number of concurrent executions exceeds the configured limit, say 2 calls at once, any additional request is immediately blocked and redirected to the fallback. And that brings us to the fallback sync method. This is our safety net. It returns a clear, controlled message when the system is under pressure. Sync fallback. Too many concurrent requests. Instead of timing out or crashing, the system responds predictably and quickly. Also notice that the bulkhead here is semaphore-based, which means the execution runs on the caller's thread. No new thread is created. This approach keeps things lightweight but requires careful control of concurrency, which is exactly what this configuration and fallback mechanism helps us manage. So in just a few lines of code, we've created a clear, resilient boundary that limits load and provides graceful degradation, all without compromising the simplicity of our service logic. Now let's turn our attention to the second example, which demonstrates the thread pool-based bulkhead, and immediately you'll notice a few key differences. This class async bulkhead service is also a Spring-managed service, but unlike our previous example, it returns a completable future, meaning the method is asynchronous. This distinction is important because it shifts the execution from the caller thread to a separate thread managed by a dedicated thread pool. At the top, we use the same bulkhead annotation, but here we explicitly specify the type as thread pool. This instructs Resilience4j to isolate the execution using a thread pool specifically assigned to this method. When a request comes in, it's handed off to that pool. If there are idle threads available, the task is picked up and run asynchronously. However, if the pool is full and the queue is at capacity, the request will not be processed. It will be routed directly to the fallback method. Inside process async request, we simulate a 3-second delay, again representing a slow or blocking operation. But unlike the synchronous version, this task does not block the main thread. Instead, it runs independently, and the response is completed via a completable future. This pattern is particularly useful when dealing with input-output bound workloads, such as external service calls or long-running background jobs, where freeing up the caller's thread is critical to system responsiveness. Now, if the bulkhead is full, meaning all threads are in use and the queue is exhausted, then Resilience4j will trigger the fallback async method. This fallback immediately completes a future with a predefined message, letting the system respond quickly and gracefully without stalling or erroring out. So what you're seeing here is a more robust concurrent isolation model. It allows for asynchronous execution, offloads work from the main thread, and shields the rest of your application from being overwhelmed by high latency operations. The trade-off, of course, is that thread pool management introduces some overhead, but for certain workloads, the benefits of isolation and non-blocking behavior far outweigh the cost. This example clearly illustrates how the thread pool bulkhead complements the semaphore-based one, offering a flexible way to build responsive and resilient systems. Now let's look at the controller that ties both bulkhead implementations together and exposes them through simple HTTP endpoints. This class, Bulkhead Controller, is annotated with REST controller, which tells Spring that it should handle incoming web requests and return the response body directly. It holds references to two services: Bulkhead service, which handles synchronous calls using semaphore-based isolation, and async bulkhead service, which deals with asynchronous calls using thread pool-based isolation. The constructor takes both services as dependencies, and Spring injects them automatically when the application starts. This setup keeps the controller clean and focused on routing traffic, while the actual logic and resilience handling remain encapsulated in the services themselves. Now focus on the two endpoints defined here. The first one, mapped to demo bulkhead sync, invokes the synchronous method. This means the request will be processed immediately on the current thread, and if the bulkhead allows it, the response is returned directly. If the limit is reached, the fallback from the sync service will be triggered. The second endpoint, demo bulkhead async, works a bit differently. It returns a completable future, which allows the request to be handled asynchronously. This endpoint delegates the execution to the thread pool defined by the thread pool bulkhead configuration. If the pool has available threads or queue space, the request will be processed. Otherwise, the fallback defined in the async service is called, and the client receives a quick response indicating that the system is under load. So this controller gives us a practical and testable interface for demonstrating both types of bulkhead behavior. Now, let's turn our attention to the application properties, because this is where we define the exact behavior of each bulkhead in our system. These settings aren't just technical configurations. They are policy decisions that directly shape how our services respond under load. We begin with the configuration for the synchronous bulkhead, identified by the name backend sync. Here, we've set the max concurrent calls to 2, which means at most 2 threads can execute the protected method at the same time. Any additional requests beyond that limit will be held in a waiting state, but only up to a point. That's where max wait duration comes in. It's set to 2 seconds. So if a thread is waiting for a slot and one doesn't become available within 2 seconds, the call is rejected and the fallback method is triggered. This gives us a controlled way to enforce concurrency limits while still allowing for short bursts or overlaps in timing. Now look at the second part of the configuration, which is for the asynchronous version, backend async. This is a thread pool-based bulkhead, and here we are managing not just how many calls can happen at once, but also how they are scheduled and queued. We've defined a max thread pool size of 3, meaning the system can run up to 3 concurrent tasks in separate threads. The core thread pool size is set to 2, which defines the baseline number of threads that stay alive even when idle. And finally, the queue capacity is set to 5, which means that if all threads are busy, up to 5 additional calls can wait in line before being rejected. Together, these settings give us fine-grained control over how much load each service can absorb, how long it should tolerate temporary pressure, and when it should start falling back. This kind of control is essential in real-world systems where different services have different performance profiles and reliability expectations. By reviewing and tuning these values carefully, we create a safety net that helps our application stay responsive even under stress. Now that our code is in place and the configuration is set, it's time to test it in the browser or through parallel requests. We'll begin with the demo bulkhead sync endpoint, which maps to our synchronous service using a semaphore-based bulkhead. Each request simulates a 3-second processing delay, and we've configured the bulkhead to allow only 2 concurrent executions. Now, it's important to note that in order to trigger the fallback, we need to send 3 or more requests at the exact same time, not one after another. Opening multiple browser tabs and pressing enter simultaneously may work, but it's not always truly parallel due to browser behavior. So for more consistent results, you can use a tool like curl in the terminal to send several requests in parallel. What you'll see is that the first 2 requests are accepted and processed, while the third and all others, if it arrives before the others finish, will be rejected after waiting up to 2 seconds. At that point, the fallback method will respond. This is a clear demonstration of how the bulkhead enforces isolation and protects the system from being overwhelmed. Now, let's switch over to the terminal and run a short script to simulate concurrent traffic to our synchronous bulkhead endpoint. I am using the built-in terminal in Eclipse, but you can run this in any terminal. The command we're about to execute is on the screen. Let me explain what's happening here. This is a simple loop in Bash, running 5 iterations from 1 to 5. On each iteration, it sends a curl request to our endpoint demo bulkhead sync. The ampersand at the end of each line is key. It tells the terminal to run each curl command in the background. So instead of executing one after another, all 5 requests are fired almost simultaneously. This gives us a true simulation of concurrent traffic, which is necessary to test the bulkhead behavior accurately. Do done is the standard syntax in Bash to mark the beginning and end of the loop body. I press enter. As we run our curl commands in the background using the ampersand symbol, the terminal immediately responds by assigning each background process a job number and a process ID. For example, when you see something like this, it simply means that this is job number 1, and the operating system has assigned it process ID with this number. This helps the shell track each background task independently. Now, as the responses come in, each line in the terminal will contain either a success message or a fallback message. If you recall, our service response was processed by sync thread name when it succeeds, and sync fallback to many concurrent requests if the bulkhead is full and the call gets rejected. In the output, the thread names you see help us understand which request was actually processed by the service logic. If you see a fallback message, that means the request exceeded the allowed concurrency, waited up to 2 seconds, and was then rejected, just as configured. By analyzing the mix of success and fallback messages in the terminal, you can see precisely when the system reaches its capacity and how it recovers gracefully instead of failing unpredictably. This is the bulkhead in action, letting through just enough traffic while shielding the system from overload. Now, when I press Ctrl and C, we might expect everything to be cancelled, but that's not quite the case. Since the curl commands were launched in the background, the interrupt signal sent by Ctrl+Z doesn't affect those background processes directly. It just returns control to the shell. Once those background requests complete, whether successfully or not, the terminal shows a summary of their completion, indicating that the job has finished and displaying the original command. So you're not terminating those curl calls, you're simply stepping back from the terminal while they finish on their own. Now let's move on and test the demo bulkhead async endpoint, which is protected by a thread pool-based bulkhead. This one behaves quite differently from the synchronous version we tested earlier. When the request comes in, it isn't executed on the caller's thread. Instead, it's handed off to a dedicated thread pool. The system then checks if any threads are free. If yes, the task is picked up and processed. If not, the request doesn't fail right away. It goes into a waiting queue up to the limit we defined in the configuration. But here's the important part. Once both the thread pool and the queue are full, any additional requests are immediately rejected and the fallback method is triggered. To properly simulate this behavior, we again need to send a burst of requests concurrently. So let's open the terminal and run the following command. Let's now interpret what we're seeing in the terminal output and connect it to how the thread pool bulkhead is actually configured. In our configuration, we've specified a core thread pool size of 2 and a maximum of 3 threads. That means up to 3 threads can run tasks in parallel at peak load. In addition, we've allowed a queue capacity of 5. So altogether, at most 8 requests can be accepted at any given time, 3 actively processed and 5 waiting in the queue. Now, when we fire 10 requests simultaneously using the loop in the terminal, what we're seeing makes perfect sense. The thread pool handled 3 of those requests immediately. 5 others were placed into the queue, waiting for a thread to become available. But the last 2, requests 9 and 10, arrived when the pool was already full and the queue had no more space to hold them. As a result, they were rejected by the bulkhead and the fallback method was triggered. So to put it simply, Resilience4j did exactly what we asked it to. It processed what it could, held what it was allowed to hold, and cleanly rejected the rest without letting the system get overwhelmed. This is precisely the kind of intelligent throttling the bulkhead pattern provides, and seeing it unfold in real time gives us confidence that our configuration is actively shaping system behavior under pressure. When we talk about applying bulkheads in microservices, we're really talking about designing systems that can survive partial failure. And in distributed architectures, this is not a theoretical problem, it's a daily reality. One service failing should not, and must not, drag others down with it. That's where bulkheads become more than just a technical pattern. They become a mindset for isolation and resilience. The first and most important principle is to apply bulkheads around external dependencies. If your service is calling out to another system, a remote API, a database, or any input-output bound operation, that's where things are most likely to go wrong. By putting a bulkhead around those calls, you ensure that if that dependency becomes slow or unresponsive, it won't consume all your available threads or block other unrelated requests. But bulkheads also apply within the boundaries of a service. In a typical microservice, there may be multiple endpoints or functional areas, some public-facing, others internal. Not all of them are equally critical. Some are latency sensitive, while others can afford to wait or degrade. The idea is to divide your internal resources accordingly, perhaps by creating separate thread pools or limiting concurrency per endpoint, so that one part of your service becoming overloaded doesn't starve the others. It's also important to tune your configurations with real-world load in mind. Don't just pick arbitrary numbers for thread pool size or max concurrent calls. Use metrics, observe behavior in staging, and adjust accordingly. And of course, always pair your bulkhead configuration with proper fallbacks. A bulkhead without a fallback is like a door with no handle. It stops the flow but gives no way out. A well-designed fallback ensures that even when capacity is exceeded, the system responds gracefully, giving users a predictable experience instead of an error or silence. Finally, never forget that bulkheads are just one part of a broader resilience strategy. They work best when combined with circuit breakers, time limiters, and retries. Together, these patterns form a layered defense, one that helps your microservices remain stable, responsive, and predictable even in the face of latency, overload, or failure. That's the essence of resilient system design. That's all what I plan to discuss with you in this lesson. Let's recap what we've learned today. We started by understanding the core idea of the bulkhead pattern and why it's essential for isolating failures in modern systems. You explored real-world examples that demonstrated how bulkheads help prevent cascading failures under high load. We compared semaphore-based and thread pool-based bulkheads and discussed when each approach is most appropriate. I showed you how Resilience4j implements both types and how you can configure them easily within a Spring Boot application. Then we reviewed a live demo that illustrated how the system behaves under concurrent load and how fallback logic is triggered. And finally, we discussed best practices for applying bulkheads in microservices to keep your architecture resilient and responsive. That's all for this lesson. Thank you so much for your attention. Have a great day and see you in the next lesson.